Okay, so let's kick it off. My name is actually Kenny Sum. So this experiment, the whole experiment and the paper was primarily done by my colleague, Pradeep, but he wasn't able to travel this time. So he's based in India, in Pune. So our team, so I work with Veritas. I think a lot of people here have heard about the name, hopefully. Used to be a big name, but we're now doing a lot of new stuff, especially in the unstructured world, in unstructured data world for NAS and all the other software and appliance functions. So, but one common issue we usually run into is now we're dealing with so many different types of workloads, some of them being complex in its own nature. Some of them are newer ones, for example, like the IoT stuff, big data, and also this non-SQL database. So those kind of new age workloads, they're pretty different from one another. So when we want to deal with all of the workloads using our existing storage systems, the same parameter settings or tunings may not always work the best way. If you want to get the best performance, the best efficiency you want to achieve for the resources you're investing for the applications. So we run into that challenge that sometimes we have to tune either the file system or the storage system itself in order for it to work the best with the given workload you have. So in the end, we're missing some of the SLAs because either the storage system wasn't tuned in the most optimal way, or because we didn't know quite enough about the application. Because now if you look at the current infrastructure we're dealing with, it's no longer just SAN, everything sitting in a data center with big boxes, with fans quite loud and cold, right? Sometimes it's in the cloud, and sometimes it's in hybrid cloud, or it's a local private cloud. But regardless, we're dealing with very different infrastructure than we were in the past. Because to start with, I think many of the applications, when we deal with them, we design the infrastructure specifically for those applications. So for example, for Oracle database, we know, hey, just put a bunch of storage array together with a switch in between and then connect to the servers. We run all the Oracle databases on the servers, and we know the array is going to deliver whatever we want, right? But today, we're using this common virtual layers of infrastructures trying to deal with all kinds of different workloads. So when you do this, you may not always be the most optimal configuration. So with that said, in order to meet all the changing requirements of all kinds of workloads, we need something to be smarter, right? So whenever you come across a new workload, you should be able to, for example, recognize what type of workload it is. And as long as you can do that, then you can take actions according to either your policy or a predefined profile to pre-adjust your storage system so that it will always perform the most optimal way according to the workload you're running. So let me give you a maybe not so good analogy. Let's say, I believe some of you may have your favorite restaurant, right? So if you remember a thing like this, when you walk into your favorite restaurant and immediately the waiter over there, he or she recognizes you. They say, hey, hello, Mr. or Mrs. somebody. Welcome again. I know you're going to order something. We got it ready for you. That's kind of feeling you would like, because just on a side note, one of that favorite restaurant for myself would be Carl's Jr., which is kind of strange, but I like the way, after like a long session of meeting, sometimes you need a comfort food. When you walk in, you don't even have to order. Somebody already did it for you. They say, oh, it's you again. I know you're going to order this, number 5, okay? We got it ready. So you just need to swipe your card and you'll be ready in a minute. So imagine if your workload can be recognized by your storage system. So whenever you attach that workload to the storage system, and then the storage system would automatically tune everything just for that application, for that workload, then you don't have to worry about a thing, right? You always can rest assured that your workload can run, your application can run at the best performance possible, but with the most efficient resource investment. So with that said, I'm going to set the stage. We did an experiment in this talk. We actually used a machine learning algorithm, try to recognize different workloads by their unique DNAs. We can call it DNA, can call it signature, whatever that is. Basically, we build a program. It's a model, machine learning model. So what it does is when you fit a workload into that model, it'll tell you what exactly that is. And once you have that, you can, be my guest, define all of your policies, tunings, parameters of your storage system to suit that workload. So this talk is about to focus on the first step to recognize those workloads, differentiate one from another. Right? So we're using 6 different workloads in our experiment. So you have the virtual desktop infrastructure, and you have this VDA. It's basically this data is a video archive workload, and there's a software build, database, mail server, file share. Pretty much covers some of the traditional workloads, but with newer workloads, it's the same thing. So once you have this workload, you can train this model using this new workload. And the training process using our model here in this example doesn't even take a few hours. It's probably 3 hours top. But once it's trained, you can take this pre-trained model and deploy it in your production system. But I don't want to limit the possibilities, but that's one way you can apply that. We'll talk about that later. So we already went through this part. So you can see that we're trying to identify, hey, what exactly is running over there. So before I jump into the machine learning part, I just want to do a quick poll. How many of you have working knowledge about machine learning or are dealing with machine learning on a daily basis? I see quite a few. That's actually a relief. So maybe I just ignored the questions from you guys. No, just kidding. OK, so the overview is basically we're using the supervised neural networks. So I explained that a little bit later. It's 4x3 and use the 5 system counters as input. So while forming this input vector, we're using all these counters from 5 system statistics output. And also these counters, the set of counters, actually there are many counters. There are over 200 counters for any 5 system statistic report. But we're using a subset of that counters to form the DNA. It's the signature of each workload. So I'll plot that on the graph so you'll see what that looks like in a minute. And then using that DNA fit into the model, and the model would actually tell us what it thinks the workload might be. And with a probability rating. For example, 96%, I think that's a VDA, right? So I guess whoever raised your hand just now can ignore this part, but I'm just going to use a very simple example to explain how the supervised neural network works in this case. So this supervised neural networks, or in short, SNN, I think we use so many terminologies nowadays, is basically one of the very popular machine learning methods that are commonly used nowadays. Usually, when we say supervised, you think about children, kids, right? The supervised learning is basically you know what exactly you are expecting, but you want to teach the model that you are training, look, I know what you should tell me. When you see a cat, you should say cat. But if you don't say cat, I'm going to tell you you are wrong, right? I'm going to correct you every time until you successfully realize, hey, that's a cat. That's not a dog. That's not a puppy, right? So that's a supervised way of training this model. So on this graph, you can see there are many dots. And there's a star pattern. There's a cloud pattern. So the actual network part is in the middle part of all the dots with the arrows pointing each other. So how it works is basically on the left-hand side, you have your inputs. It's basically whatever features you want to feed into the model. So the purpose of this training is eventually, after feeding those features, inputs into this model, it'll be able to calculate within this own network and eventually reach the right-hand side, the 2 dots on the right-hand side, and give each dot a value, right? So the value can be anything 0, 1, or anything between that. So if it says, after all the calculation in between, if it says on the pattern star circle, the dot, it says 0, and on the pattern cloud dot, it says 1, it means that the model thinks, based on its calculation, that the input you fed it was a pattern cloud instead of like a pattern star. But in order to do that, it has to go through the entire cycle of feed forward and also this back propagation, adjusting the weights. We'll go through all these terminologies in a minute in the next slide. But right now, you have to know, this network itself is not that smart. So when we go through the process, how it works, you realize actually every step is just taking very random guesses to begin with, right? So let's explain that a little bit in the next graph. So here you can see a slightly more complex graph, but with the same kind of design, similar design, I would say. So on the left-hand side, there are 3 input nodes, and with 2 layers of networks in between. Usually we call those 2 layers the hidden layer, the hidden part. On the right-hand side, there are 2 output nodes. The output nodes are actually the prediction part. So you want to feed all of your different features into the left-hand side 3 nodes and let it go through the entire calculation following all the red lines and eventually contribute to the value in the rightmost layer with these 2 output nodes. And eventually, it'll give you this 2 value. And now it's time, if you look at the right-hand chart, now it's time to compare. And that compare is done, for example, by you as a supervised learning. It's time for you to tell this network by looking at these 2 numbers, for example, 0.4AA1 and 0.5119, and tell how accurate that prediction was. For example, I give you a very simple example, which is also commonly used. Let's say we want to train this network to recognize animals. And animals, each animal, let's keep it simple to mammals, they have different features. Let's say the fur, yes or no, has fur or doesn't have fur, right? And if has, then fur color, for example, weight, height. There are so many different features for a given mammal, an animal. So each individual feature can be one of the inputs on the left-hand side. So in this case, we're only using 3 inputs. Let's say fur color, weight, and maybe can it make a sound, for example, like that, right? And then you give a value for each of the individual feature. Let's say fur color black is 0, white is 1. Let's just start with 2 colors to make things easy. So then the weight, we can say it's heavier than 5 pounds or is less than 5 pounds. And does it make sound, yes or no? So with those features, of course, as a human, you cannot easily tell with only 3 features, right? But then you turn those values into number values. You can see the second layer, which is the first layer of the hidden part, with the 4 nodes from top to down, the dot 4, 6, 6, 9. So the red lines connecting the left-hand side inputs and the second layer nodes, each red line has a weight. So that weight, you can understand it this way. So for whatever value I give to the left-hand side input, I multiply that weight. And after multiply that weight, I would again plus to the value that was also assigned on the second layer node itself. That's called the bias. Yeah?
Here we're talking about workload. Okay. What are you looking into workload to generate these weights?
I cover that in the next slide. Good question, thanks. So basically, after doing all this calculation, it will give you some results, right? But in the first place, all the weights and biases are kind of randomly assigned to begin with. So because it doesn't have any idea how to predict it, you can think of it as the model took a wild guess. It guessed that if I calculate by multiplying 5, then maybe I reach the right value, right? But at the end, it'll tell the model, no, you were wrong, and you were off by 0.3, for example. And that 0.3 will be fed back into this model as a contributor to tell the model you need to adjust your weights. The randomly assigned weights weren't accurate. You have to adjust them so you can achieve more accuracy. So iteration happens like this again and again for thousands of times, for example. And after that, you will see all the red lines in this network has a more accurate weight assigned to each of them. And all of the nodes in between have a more accurate bias assigned to each of them. So after that, you have a trained model. But you don't stop until you reach your desired accuracy, which means the error, the off, how much off, is within the acceptable range established by yourself earlier. So once that is trained, then this model is complete, it's trained. You can then deploy the same model, but instead without randomly assigned weights and bias, but with trained and calculated, adjusted weights and biases, and use that to do the prediction. So that's how, in a simple way, supervised neural network works. So with that, I'm not going to dive deeper because obviously I'm not a data scientist. I know there are data scientists here. So if you need more information, there are plenty of material online for that as well. I'm just going to give you something there. So now we're coming to how to use that supervised neural networks in this use case. So how to use it to train it to recognize the workloads. So like I mentioned earlier, so we, in this case, in this experiment, we're actually using these file system counters. I showed them in the next slides or so, I think, next few slides. I show, there are overall 283 file system counters if you run like a file system stat command. In this case, we're using this Veritas file system, which has been running decades in enterprises. So one of the tools that comes with it is called the VXFS stat. So it will print out all the statistics, including all the file system counters that you can use to train this model. And once you have that counters, then you can build and engineer your input vector. So how to form the left-hand side, the first layer of nodes, how to assign values for them. So I'll cover that. So this is the collecting part, right? We collect all the 283 file system counters for each of the workloads. So which means for 6 of the workloads, we collect them 6 times. So then, the counters, you can see them as, the reflectors of the entire workload activities happening on the storage system. So they include things like, how the I/O trickles down applications to the storage system, how often it does, for example, flushes, and how often it does this inode operations or vnode operations in the memory, for example. So those counters, give you information about all the different activities happening in your storage system as a result of a given workload, right? So that's why we think it might be useful to form this unique signature for a given workload. But whether you can do that or not, we'll need to verify with this training later. So you can see these workloads, the counters were collected with a 10-second interval, and then we did some average value. After that, I'll talk about the collecting, the pre-processing next time. Next slide. So this part is actually very important whenever you want to use any machine learning in your real application, because there are many already established methods for doing machine learning and data analysis. But that part itself, programming that part, the algorithm, putting together algorithm, that part isn't the part that's going to take most of the time. This is. So you have to understand the data set you're working with. In this case, the data set being all the file system counters, 283 counters for each workload. You cannot just directly feed all that number into your network because it'll take forever to train it. You have to simplify it, normalize it, and also keep all the scale consistent, because some of the counters you see can be in scales of 10,000s or even more, but some other operations may only happen like a few times per minute, for example. So if you put all of them together, you can possibly ignore some of the lower scale numbers because they would appear like almost can be ignored noise because that's too flat, right? So what we did was we first eliminated eliminated all the unused counters. We did a cross-check between all 6 workloads and figure out there are a few counters, actually more than a few, that were not used by any or doesn't have a value from any of the workloads. So for those counters, we just get rid of them. We don't need them. Right? They won't make a difference. And then we normalize all the numbers we collected. So to do that, we actually use the max value way to do the normalization. So which means, showing the next, it's kind of, you don't need to read all the numbers. It's kind of small font. But what you can see, there are some big numbers, right? This 6 million number, for example. We won't feed that number directly into the model, but instead, we look at the maximum value for this counter and use that value as 1, for example, or as 10 in this case. So after that, we scale all the other workloads, but the same counter according to that maximum value to see how that compares to the maximum counter of any given workload. So by doing that, for example, if we take the first counter on the screen, the top left screen, you can read the number 15 is 150,346, right? So that number, if we compare that number to across all 6 workloads and realize that value was the largest, the maximum value that we ever saw across all 6 workloads, we will make that number 10. And then we'll scale all the other 5 workloads accordingly to that 10 value. So then eventually, after pre-processing, instead of using the values on the left, we land something on the right. So you can see none of the value actually exists 10 because all of them have been scaled. Right? Some values can be really small, but that's fine. So after that pre-processing, we eventually got 119 counters to be used as the input vector. So any question so far? I know it's a little bit, yeah.
Do you expect other file systems to have similar?
I do. I mean, it doesn't have to be file system counters. Yeah, but yeah, other file systems may have the same file system counter you can collect, but it can also be other things if you have a storage system that runs its own unique statistics.
Your experience tells you that there's a few that are the most important. Do you rely on the algorithm to determine that? Do you pre-bias the algorithm, or do you somehow adjust the relative weights at the beginning of input?
You can do both, actually. So if you rely totally on the model, the algorithm itself to do it, it will eventually figure it out too. But if you don't want to do that, you can give some pre-assigned weights just to make sure that one is taking more consideration than others. But you have to really be sure that you know how important that counter is compared to others.
And in your scaling example to 10, where the big numbers go down to 10, if you had a number that the maximum was 3, you would scale that up to 10 as well.
Yep.
After first preparing of data, you reduced it to 100 and some various data. And then the question is how many data you have after processing? So how many features you have as an input to the next?
That we left 119. That.
Either raw and process data. You are just you are not reducing here amount of data.
So the original set of data was 283. So we reduced the number of counters were used from that number to 119. And then we also did the scaling, so to keep all the numbers within the same scale.
Okay, this is that scale. Okay.
Yeah.
How many samples do you start off?
So we collected with a 10 interval, but probably over, I think, 1 hour or half an hour value. Yeah, but eventually, because we're going to do some average in between, so I'm going to show you some plotting on the next slide, but just to keep in mind, it's not a time series data. So this is the confusion part. So if you look at, I'm going to explain that a little bit. So if you look at the 6 workloads, each has a kind of curve plotted on the chart, right? But usually we'll assume, the x-axis is actually time. In this case, not. In this case, the x, the horizontal axis is actually the counters from 0 to 118. So in total, 119 counters. So here you can see after scaling, the highest value would be close to 10, for example, but it will never exceed 10. So in this way, as a human brain, you can start processing. By looking at this curve, I can almost, if I have a good memory, recognize one certain workload. If I keep looking, for example, the VDI workload, and focus on, almost the right-hand side next to the peak area, you can see there are many counters with repeating values, almost. That is kind of differentiating from the VDA workload, which doesn't have that pattern. So if you memorize that part by yourself, maybe without this training model, you can do the thing yourself. But that cannot be automated, right? You cannot have someone run all this stuff and reach these values and graph it, and you tell me what workload it is. But eventually, the idea is similar. So we're training a machine learning model in this case to know this is a graphic view of basically to show you the DNA of each workload. But eventually, we're going to tell the model to tell what the differences are between the different kind of workloads. And once you feed that one of the chart, not in this form, but in the number form, into this model, it's going to tell you, pretty much it's a VDA. I'm not 100% sure, but 98%. Got a question?
How close different VDI workloads, if you wanted to plot samples from different installations and put them one
Yeah, I think what you're trying to ask is, for example, if I take two VDI workloads issued by different applications, but both are VDI workloads, how close are they when it comes down to this chart, right? So according to the model and the tools we use to generate all that workload, they're pretty close. I mean, the off is like maybe 1 or 2% from the counters we selected. You mean the numbers of? It will change, yes. So which means if you're adding new workloads, you have to retrain the model, yeah. You got a question?
Yeah, so just so I understand, right? So this is not a time series, but what you're doing is all the counters that you collected over a period of 1.5 hours, for that workload, you're averaging them out and then scaling them to 1 to 10, so 0 to 10.
Yep. Yes. Yeah, but there can be other ways to do it. But I mean, in order to use this model or this method, you have to know this workload first. I mean, you don't have to 100% know exactly what it's going to do over a 1 hour time, but you have to know which counters would matter in this case. And you can eliminate some of the noises. For example, you know that operation, although it's going to differentiate from this workload to that workload, but it doesn't mean it has a very strong tie to the workload type, but maybe it's just a random value due to the condition at the time, maybe the underlying storage system, for example. So by knowing that counters, you can also manually eliminate some of the other counters that you don't want to use that is not going to contribute to differentiate the workloads from one another. So it's based on your understanding. It's not like a foolproof, just feed whatever to it and it'll tell me what it is, right? You have to bring your at least certain level of understanding and use that knowledge to engineer your data set before fitting that into this model. So in this whole exercise, I would say the most critical part is actually happening before you're fitting this data into the model. It's actually how you engineer your data. Yeah, so that'll come to the question, how do we define the model to be trained enough? So there are concepts I believe some of you have heard, like overfitting and underfitting, right? So overfitting means you train this model too much. I mean, to put it in a simple way, you train it too much so that it only recognizes a very specific instance of the workload. So VDI, for example, if you're running a VDI application, different versions will give you slightly different graph like this. But if you overtrain this model, it will differentiate version 1 with version 2, although both of them are VDI workloads, but it doesn't think so, according to the calculation. But underfitting meaning there isn't enough differentiator for you to tell one workload from another. So you don't want to do either one, which means you have to do experiments to see, and also you have to set how much confidence I want. The probability doesn't mean that the higher the better. I would say 100%, that's the best, but there's always some flexibility when you run applications, and as long as you achieve a high enough confidence level, that model may be good enough. So I don't shoot for example, 99%, I shoot for 85%. So whenever it says, on the right-hand side, if you remember that chart, the right-hand side output nodes, whenever it says one of the value being 0.85, I think that's good enough. I'm going to trust you on that, because all the other numbers are much lower than it. Does that answer your question?
Actually, my question was more to the effect of, instead of doing machine learning, just use a correlation metric. Now, whatever comes in, correlate against these guys, come up with a number, whichever is the highest. That's like the simplest.
You can.
Classify it, right?
Yes, I think in. So why?
Say that each of these workload graphs are fairly reproducible, well reproducible.
Mm-hmm.
So in that case, wondering if that's sort of a simple.
Yeah, it's reproducible with variation and flexibility. So it's not like reproducible to be exact every time. So when you have the slightly variation in between, that's where you want to use something like a machine learning instead, like a static algorithm or a matrix to figure out. Because that's a difference between one-on-one mapping and 1 and maybe 0.85 mapping. Right? So this chart actually summarizes the process. So you can see from the left-hand side, we have this real-world workload. And after sampling and pre-processing, we reach all the counters, scaled counters. So just a quick note here. So this graph for each workload is not required for machine learning. It's only for us to understand how it works, right? So it's not that it only works with image, right? It's all numbers. But we're using that so we understand how it recognizes each workload by its signature. That's like a signature.
So is Veritas using this in their product right now?
Not yet in this specific case, but we do have dedicated team on machine learning, and there are some other application. Yes.
Okay. These workloads look like spec, SFS?
Some of them, yes.
Is that what you use?
Yeah, some of them we use the spec SFS, I think 2014. And there are others like FileShare and mail server. We also used other real-world workload as well.
Yeah, okay, so you've done real-world workloads. Do you got anything, an example that shows us that correlation?
Yeah, I probably need to take that question back to the team. But I believe a similar method, if we applied it for a real-world workload, which means if we train this model using another workload, let's say Cassandra, then it's able to generate a different graph than that one, and we can use the same model to identify Cassandra workload, for example. Okay, so the training cycle actually, it's because it was an experiment, we didn't use like a ton of data for that. We only took like 5 pre-processed input vectors, which means we run each workload 50 times, each time for certain hours. And then we have this 50 sets of input vectors, and we use that to train this model again and again until we reach the desired probability level. So basically the confidence level is good enough. The error is low enough, then we think it's good. And then We actually experimented with different network configuration as well. So in this case, 3-layer, 4-node in each layer was found to be good enough for this type of work. So we also did some experiments with smaller configuration and larger configuration. But eventually you have to find a balance between your computing power, time, as well as your use case. In this case, how many input vectors, how many features you're taking into consideration in your input vectors, and how many output you are going to generate. In this case, the input is 119 and output is 6. So ideally, we should usually use numbers between input and output. So you can do more variations and make sure the back propagation goes well. But in this case, we used a simpler configuration, and it turned out to be efficient enough. So we didn't try with a much complex configuration.
Can you give us a little bit of insight on best practices or rules of thumb that you're starting to develop, to get to 3-layer, 4-node? How do you, before you know that that's what it's going to be, how do you sit down to bound the problem, where you're going to start, where you're going to finish?
So that question, I think it's more about how do we design the network, right? So how do we land to that configuration?
And does the range of input or the number of things you're classifying for, have you developed some rules?
So we haven't, but there are several rules of thumb. Usually, I believe the people here may have better idea than I do. But there are a few of them. I can, maybe one example would be consider your input, the input and output, and make sure but you better use a number of nodes in the hidden layer that is between input and output. So you don't dramatically enlarge the input or reduce the input at the first layer, and you don't do the same thing with the output before generating the data. So for example, if you're dealing with 3 input, as we mentioned in the example of animal recognition, right? For example, identification. So if you're using only 3 inputs vectors, but the output is only 2 between 2 animals, then you may not want to use like an 8-node configuration because that won't be required. It's a very simple problem. But if you're dealing with, let's say, we're going to differentiate between 500 different types of animals, you don't want to use a 2-node, maybe 3-node. You want to use more nodes, closer to your ends, the left hand or right hand. But you have to maybe run some experiment to figure out what's the best and what's the most efficient configuration that you should use. And it also depends on the feature engineering you're doing. But I think some of the data scientists here maybe have a better answer on that. So I would encourage you to maybe look into that problem and find out whether there's a better way to configure the network in this case. So the training cycle, we already talked about it. So I think it's, is there any other question on the training, how it's done?
Yeah, so once you deploy it, do you continuously update things?
No. So in this case, once it's trained, we deploy the pre-trained model as it's kind of like an application. So it's a Python. You can think of it as a Python program with already adjusted weights hard-coded into the program. So whenever you run this program, it'll give you its prediction. You don't have to adjust it. You can change the program to make it constantly training, but it'll burn you more resources as well.
Training, what's the methodology and what was the order of training? So did you do training of your brand new network against first workload, and then backpropagation, second network propagation, third, and so on?
Yep. We train, so in total, I'd say 50 times for each workload, which means the 300 inputs, actually. So we train the model 300 times using different inputs, regardless what workload that was.
But in this order, right? So the first, second, third, fourth, fifth, sixth workload, and then again, third, second, etc. Not 50 times first workload, 50 second. What order?
So yeah, we sample that every 10 seconds, and we get this counter for each workload. That's only one set of data. We do that 300 times. And each set would give us 119 numbers to use as the input vector. Yeah.
with 100 some inputs and 6 outputs,
Yes.
right? And the flow of training, so you have just brand new network and you are training this against first workload, first iteration of first workload, and you are getting something on outputs, then you are doing backpropagation flow, and then another step is to take second workload against this already modified network to get results, backpropagation, and so on, right?
You can use the same workload too. I mean,
but the question is, matters or not?
It's not much. Yeah.
No.
So because eventually you want to teach the model to know all 6 workloads. It doesn't matter which one you train it first, but yeah.
Yes, but my question was, if you are doing 50 iterations of training against first workload, then you go to...
Yeah, I get what you're saying, yeah. Then you have to, you can do it 50 times using the same workload. That'll make sure whatever weights it lands on, it'll give you good enough, a prediction on the first workload. So as a result, for example, if you only train it 50 times using only one workload, you probably have a very high, very close value than your expected value for that type of workload on the output. So on the output, we have 6 nodes, right? So eventually, we will be expecting, in the ideal case, a number 1 on one of the nodes and number 0 on all other 5 nodes. So if you only train it with one workload for 50 times, then ideally you would end up with, a number 0.95, for example, on one of the nodes, and some small number or even not small number on other workloads. It may be larger number because you haven't trained that part yet. Yeah, but then at least you have a very close number to your expected 1 at the given workload. If you train it with VDI, you should see a number after that training very close to 1 on the VDI node in your output. And once that number is close enough, you call it trained for that workload. Then you can proceed with other workloads. Yeah, testing is actually more, it's more straightforward. You just fill it with, again, real-life workloads, or even workloads or benchmark workloads, whatever that is. If you believe that's the same type of workloads, when I say same type, it doesn't mean that you call it the same name, right? Sometimes, although people think 2 workloads are similar to each other, they're not. So whether it's similar depends on the signature, the DNA, the graph. If that's totally different, then it's a different workload, right? So if you run the same workload again, fit into the model with already trained, which means already adjusted weights, then you should see eventually on the right-hand side of basically the output part, you should see one of the numbers close to 1. And that's going to point to which workload that is. So this is an example. If you run it with a workload in the testing part, you will see, for example, you fit it with a VDI, then the output would tell you it's 97.97 VDI, and with a very small number on other workloads possibility as well. But eventually, it's up to you how close you want to get, right?
So if you wanted to increase the accuracy further, what would you change?
You train it more with more iteration, more input. Yeah, collect more data and train it again and again and again until it gives you a better number.
Actually, one more question. So where did you deploy this? As in, does it? I'm more interested in how much it
Application or
performance decreases.
yeah. So I don't think we have done that part yet, but I have talked about it briefly at the last slide on that.
What do you expect? What is to happen if you run 2 workloads concurrently?
That's a good question, and we had that question internally as well. So basically, if you run 2 workloads at the same time, right, eventually what you collect in the counters would be, it's kind of like a mixture of 2. So if you have high values on counter 1 for workload 1 and high values on counter 2 for workload 2, then eventually you will see high values in both counter 1 and counter 2 if you run both workloads together. But then the question becomes, how much of first workload you're running compared to the second workload. let's say you can run 90% first workload and 10% second workload. So that becomes a more complex question. So this model that we trained is only good to tell one pure workload running at one time. But if you want it to detect multiple workloads running at the same time, you have to train it that way, and so that it can recognize, in certain scenarios, a mixture of two. You will probably see not such high number on VDI and VDA, for example. You will probably see, for example, 0.6 on VDI and 0.4 or 0.5 on VDA, and other numbers being very minimum. But there are coincidences. For example, two workloads added together, it yields a result that's very similar to a third workload. So when that's the case, you have errors, right? And if you know that's an error, you feed that back into the model, then it tells you, no, that's not the third workload. That's actually a mixture of 1 and 2. You can keep training it that way. Yeah, but eventually, there's no guarantee that this network will give you close to 1 confidence always. It depends on the actual case. Sometimes you can never get that accurate unless you're overfitting.
So it really depends on what you want to do with it, right?
Yeah.
Because you have 6 different workloads. It can be named ABC or whatever, right? It doesn't matter. So the whole idea, if I understand correctly, is to do some optimizations within your storage layer based on what type of workload you observe. So if your combined workload is of type A, right? That's good enough to do the optimizations for workload of type A. It need not be for VDI or VDA. It can be
So the conclusion of this experiment is actually, sometimes such small neural network configuration can be trained and used to identify workloads based on, its own activity patterns. And it has a very high success rate based on this experiment. Of course, it depends on how you configure and train this workload. It may give you different results in different use case. But eventually, once this model is trained, then you can almost take in time, real-time actions, because once trained, you don't need to burn that much computing power again once you deploy that pre-trained model into your application. So once it sees already seeing workload, then it'll immediately tell you, hey, this is the VDI, this is the VDA. And from there, you can define what actions to be taken, right? So that's one scenario where you can applicate it. I'm not going to talk about all the other possibilities, but there are a few things that we thought about, but there are endless other possibilities. You can use it to detect anomalies. For example, that's a VDI workload, but for some reason, the workload, once it reaches the storage system, it doesn't generate the same pattern anymore, then something must be wrong. And you have to figure out what was wrong, right? Network was wrong, storage itself, or something else. And it can take actions to improve application performance, SLAs. You can also schedule, resources. So for different workloads, for example, some of the workloads may require faster tiers like SSDs. Some of the workloads are more transactional, or some of the workloads are, So depending on the different requirements for each workload, once you recognize what the workload is, then you can schedule resources accordingly.
further thoughts on what kind of proactive actions you could take for improving that?
So I will give you an example. It doesn't have to be like a production-ready example, but there was an intern project that we did this past summer. So we built a thing called like a smart tune. It's also based on machine learning. So you can imagine if we take this model into that project, then what it does is once it sees a VDA workload coming in, I'm going to automatically tune my file system and underlying storage system to meet the performance requirements for that workload. For example, I can change my allocation unit size. I can change the cache behavior. I can define how often it flushes. For example, all those things can be tuned. And the tuning, as in the profile, can be decided according to your detection, right? So that's the action as an example. But there are other possibilities. So this is not like a production ready, you can just take it in your application and run it. This is more like an inspiring idea, so you can know that there's something possible if you want to learn machine learning. There's something possible that you can do to take advantage of this, machine learning algorithms to give you more knowledge and control over your applications and workloads. Okay, that actually concludes my presentation. I hope you enjoyed it. It's the last session. Thanks everyone for showing up and asking all the